In this video, we take a look at subspaces of vector spaces. We are going to see the definition and some theorems, and also examples of subspaces and examples of spaces that are not subspaces. So this is chapter 4.3, and our learning objectives are to determine whether a subset W of a vector space is a subspace of the vector space V. And our other objective is to determine some subspaces of Rn. So many vector spaces are actually subspaces of larger spaces. So we say a non-empty subset W of vector space V is called a subspace of V when it is a vector space under the operations of vector addition and scalar multiplication defined in V. So our same operations we've been working with, vector addition and scalar multiplication. So theorem 4.5 tells us how to test for a subspace. So if W is a non-empty subset of V, then W is a subspace of V if and only if, so remember everything has to be true and if and only if, the following conditions hold. W is not empty. If U and V are in W, then the sum U plus V is in W, so that's closure under addition. And if U is in W and C is a scalar, then C multiplied by U is in W, so closure under scalar multiplication. So here's our proof. If W is a subspace of V, then W is a vector space satisfying the closure axioms. So U plus V is in W and C, scalar C multiplied by U is in W. So if we know W is a subspace of V, then those properties are held. So now we have to go backwards, assume the properties are true, and show that W is a subspace. So we are going to assume W is closed under vector addition and scalar multiplication. So by assumption, then our two axioms are satisfied. The sum of two elements is also in W, and scalar multiplication by a vector is also in W. Then if U, V, and W are in W, then they are also in V. So the following axioms are automatically satisfied: the commutative property, the associativity property, the distributive property over vector addition, the distributive property over scalar addition, the associative property, and then the scalar identity. So because W is closed under scalar multiplication, we know that for any V in W, 0 times V and -1 times V are also in W. So from theorem 4.4 back in the earlier videos, we know that the 0 scalar times vector V is the 0 vector. And we know that the -1 scalar times vector V is negative vector V. So the remaining axioms 4 and 5 are also satisfied. Our space W contains the 0 vector, and for every V in W, W contains -V. So we have satisfied this theorem that if W is a non-empty subset of V, then W is a subspace of V if and only if these three conditions hold. All right, we are going to look at examples of subspaces and examples of sets that are not subspaces. So we want to show that the set W, which is V1, 0, V3, so a 3-tuple here, where V1 and V3 are real numbers, is a subspace of R3, the set of all 3 tuples with the standard operations. So graphically, because Y is always 0, W is in the XZ plane in R3, or it is the XZ plane here. So in our drawing it right, we see the plane going through XZ. W is non-empty because it contains the origin for sure. W is closed under addition because if U and V are W, then U plus V, if U is these components, U1, 0, U3, and V is the components V1, 0, 3. The sum is going to be in the first component U1 plus V1, 0 in the second component, and U3 plus V3 in the third component. So we still got a 0 for the second component, so we're still in the XZ plane. So the addition is still in W, so we're closed under addition. And then W is closed under scalar multiplication because a scalar times 0 is still 0. So if you multiply through by a scalar, your element is still in the xz plane. So C times V1, 0, V3 is just C times V1, 0, and C times V3. So we still are in the xz plane because y, or the second component, is still 0. All right, let's look at another example. Is Z2 the ordered pair of integers with the standard operations of a subspace? Is that a subspace of R2? So here is what this would visually look like. You'd have points at all the ordered pairs of integers on the xy plane. So Z2 is closed under addition, right? Because if you add an integer to an integer, you stay an integer. But as we saw back in section 4.2, Z2 is not closed under scalar multiplication, because if we multiply a fraction or a non-integer by the integers, for example, a half times the ordered pair 1, 2, we get ordered pair where one element is not an integer. You get ordered pairs where both elements are not integers, so they're not in Z2, the ordered pairs of integers. So Z2 is not a subspace of R2. All right, in our next example, we want to show that the set W equals the ordered pairs V1, V2, where V1 is 0 or V2 is 0 with the standard operations is not a subspace of R2. So W would be closed under scalar multiplication, because if you multiply a scalar through, you're still going to have one of the elements be a 0. But W is not closed under addition. So for example, if you've got 1, 0 plus 0, 1, then you get 1, 1, where neither element's 0. So that is not in this subspace where one of the elements or components has to be a 0. And so you can visualize that actually you can think about it as the x-axis and the y-axis, right? Because those would be all the places where either the first component is 0 along the x-axis, or I'm sorry, along the y-axis, or where the second component is 0, which would be along the x-axis. Okay, so now we're going to investigate the set where W equals the ordered pairs V1 and V2, where they're both positive. So that's what we think about as the first quadrant, shaded over here in the diagram. So is that set with the standard operations a subspace of R2? So this is closed under addition. If you add something in the first quadrant, positive values to positive values, you're going to stay positive. But it's not going to be closed under scalar multiplication, because imagine if you multiply by a negative scalar. So if our scalar C's are less than 0 and V is not 0, then you're going to end up in a different quadrant visually. So for example, if you've got -1 times the ordered pair 2, 3, then you get -2 and -3, which would be over here in quadrant 3, which is not in our set W. So in general, when you're visualizing subspaces, you can think about the subspace as being a straight line or a flat, like a plane, or the higher dimensional equivalent of a plane, right? A straight line is in 2 dimensions, a plane is in 3 dimensions. We can only imagine what 4 dimensions subspaces look like. But so a subspace has to be infinite in all directions, has no holes, and contains the origins in those scenarios. All right, now we're going to let W be the set of all symmetric 2 by 2 matrices, and we're going to show that W is a subspace of the 2 by 2 matrices with the standard operations. Okay, so A is symmetric, meaning A is a symmetric matrix, means that A equals A transpose. So W is not empty. There are symmetric matrices that exist for the 2 by 2 matrices. For sure, we can say it contains 0, 0. W is closed under addition, because if A and B are in W, then A plus B transpose, we know that's going to be, by matrix properties, A transpose plus B transpose, which is just A plus B. So A plus B is also symmetric. So note that when we showed that it was not empty, you just have to show one element. Usually we show the 0 element. It's the easiest to show right here. So you don't have to show more than one element to prove the non-empty part of our 3 criteria to hold our 3 conditions. So for that zeroth condition, usually you show the 0 element is in there or whatever is equivalent to that. All right, so now we're going to prove the third element. If U is in W and C is a scalar, then the scalar multiplication is also in W. All right, so if C is a scalar and A is a symmetric matrix in W, then C times A transpose, well, that C comes out front and it's just C times A transpose, which is just C times A. So C times A is symmetric. So W is also closed under scalar multiplication. So we have shown all three properties. And so we can say that the set of all symmetric 2x2 matrices is a subspace of all 2x2 matrices. Now we let W be the set of all singular matrices of order 2, show that W is not a subspace of the 2x2 matrices with standard operations. So remember, singular matrices are when the determinant equals 0. So here are two singular matrices, 1, 0, and then 0, 0 in the second row, and then 0, 0 in the first row, and 0, 1 in the second row. So these are singular because their determinants would be 0. W is not empty because B exists. But if you add these up, you get something that's not singular. You get 1, 1 on the diagonal over here, and you've got a matrix now with determinant 1. So W is not closed under addition, and it's therefore not a subspace. All right. Notice that W is written symbolically as, you know, the 2x2 matrix with elements A, B, C, D, such that AD minus BC equals 0. And notice that AD minus BC equals 0 is not a linear equation. All right, on to the second bullet. We're going to let W now be the unit circle in R2. So in other words, we can say symbolically that W is the set of ordered pairs such that the first component squared plus the second component squared equals 1. You could think about, in our usual notation, we'd say the unit circle is x squared plus y squared equals 1. So here we're just saying V1 instead of x in V2 instead of y. And we're going to have the standard operations. So is W a subspace of R? Well, think about under addition. So if you have, you know, 1 squared plus 0 squared equals 1, and 0 squared plus 1 squared equals 1. If you add those up, you get 1, 1, but 1 squared plus 1 squared is 2, which is not the unit circle, not in W anymore. So it's not a subspace. You could find another reason that W is not closed under scalar multiplication. If you multiply a 0 through, you get zeros, which are also not in W. Moving on to our third bullet. Is W equals 0, 0 with the standard operations a subspace of R2? So the origin in R2. And yes, because the only addition to check is that 0 plus 0 equals 0. Scalar multiplication is also easy to check. C times 0 is also 0, which is in W. So W equals the 0 vector is called the trivial subspace of V. The other trivial subspace is if W is all of V. So we say there's two trivial subspaces, the 0 vector, and then the subspace where you're actually just the same space. So if I said W equals R2, you already know R2 is a vector space. So of course it's trivially a subspace. Okay, moving on. Which of these two subsets is a subspace of R3 with the standard operations? So our first choice here is the subset U with the 3 tuples, where the condition satisfied has to be that 2v1 plus 3v2 plus 4v3 equals 12. And if it makes you more comfortable to say x's and y's instead here, anytime you're working with elements, you can always replace your conditions with the more familiars, x, y, and z. So if you wanted to say, oh, this is just all the x, y's, and z's such that this equation is true, that's fine. We like to use, subscripts for V's or U's or X's because it's easy then to extend it to n dimensions. If we go to like 4 or 5 dimensions with X, Y, and Z, we're at the end of the alphabet. So we don't have any more letters to use. So that's why at this point we tend to use indices. But if you're working in 2 or 3 dimensions, feel free to shift to X and Y or X, Y, Z if that's easier for your calculations and visualizations. Okay, so this is the equation of a plane, and the plane goes through the point 6, 0, 0. You could check because 2 times 12, if V1 is 6, 2 times 12, 2 times 6 is 12. It would also go through the points 0, 4, 0, and it would also go through the points 0, 0, 3. And so we see that right here because all of those would give us equality to 12. So this space is not closed under addition because if you add all these 3 points up, then you get things that are no longer in that plane. So if you add up, the first 2 points, 6, 0, 0 and 0, 4, 0, now you've got this point 6, 4, 0. But now if you plug those values into the equation, 2 times 6 plus 3 times 4 plus 4 times 0 is 24. It's not 12 anymore. And then this is also not closed under scalar multiplication. So think about if you use the scalar 0 and multiplied it by the point 6, 0, 0, now you've got all zeros, which put in the equation adds up to 0, not 12. So you don't have to show both reasons. Once you show one of these reasons, that's enough to show that U is not a subspace. Now in part B, we're going to think about this subspace W. So again, we've got 3 tuple in R3, V1, V2, and V3. And now we're satisfying this equation, 2V1 minus 3V2 plus 4V3 equals 0. So this is the equation of a plane that's parallel to U, but now W contains 0. So before, if we put in all zeros up in U, we didn't get a sum of 12. Here in W, if we put in zeros for V1, V2, and V3, then we get a sum of 0, which is in W. So if V and W are in W, then V plus W is going to add up to be V1 plus W1 in the first component, V2 plus W2 in the second component, and V3 plus W3 in the third component. And then 2 times V1 plus W1 minus 3 times V2 plus W2 plus 4 times V3 plus W3 equals all of this here. 2V1 plus 2W1 minus 3V2 minus 3W2 plus 4V3 plus 4W3. And then we can rearrange to show that, oh, well, that's just V in the equation plus W in the equation. So those are both zeros. So 0 plus 0 is still 0. So the sum is still in W. And then if C is a scalar, think about if you multiply the scalar through each component, you can pull the scalar out front, and then it's just a scalar times 0, which is still 0. So scalar multiplication is also contained in W, so W in this case is a subspace. So the big difference between these two examples is that part B contains the origin 0, 0, 0 because the equation was equal to 0, but in part A, this was equal to some other number. So we saw it wasn't closed under scalar multiplication or scalar addition. Okay, we're going to look now at P, where P contained in the interval 0, 1 is the set of all real valued polynomial functions on the domain 0, 1. Notice it's a closed domain. We could say C with a 1 up in the superscript on the domain 0, 1 is the set of all real valued continuously differentiable functions on the domain 0, 1, the closed domain. And then C to the 0 superscript of that interval 0, 1 is also sometimes written as C of the interval 0, 1, and that's the set of all real valued continuous functions on the domain 0, 1. So the difference is when we say C with a 1 up there, those are continuously differentiable. So we're going to let W be the set of all real valued integrable functions on this closed interval 0, 1. And we're going to let V be the set of all real valued functions on this closed interval 0, 1. So if we take the usual definitions of vector addition and scalar multiplication, and we use the real numbers as our field of scalars, then V is a vector space, and the other 4 sets are subspaces of V. So it makes sense that integrable functions would be subspaces of all the other functions. Polynomial functions are subspaces of all the other functions, and continuously differentiable functions are subspaces of all the other functions. So in fact, we can say the set of all real valued polynomials on the domain 0, 1 is a subspace of all the continuously differentiable functions on 0, 1, because we know polynomials are continuously differentiable functions, but they're not the only continually differentiable functions. Think about C superscript 1 of 0, 1 would also contain sine, cosine, e to the x. So the polynomials are just a subspace of that. And then that's a subspace of just all the real value continuous functions that we denote C with a superscript 0, or more often just C 0, 1. And so that's a subspace of all real valued integrable functions. And then all the real valued integrable functions are subspace of just all the functions V on that closed interval 0, 1. So that brings us to theorem 4.6. So we can think about the intersection of 2 subspaces, and that is also a subspace. So if V and W are both subspaces of a vector U, then the interaction of V and W, or intersection, I should say, denoted V, this arch means intersect, hopefully you've seen it before, V intersect W, is also a subspace of U. So note that V intersect W, which we visualize here in the middle of the Venn diagram, is a set of all vectors that are in both V and W. So here's our proof. Because V and W are both subspaces of U, we know that they both contain 0. So V intersect W contains 0, so therefore it's not empty. To show that V intersect W is closed under addition, let U1 and U2 be 2 vectors in V intersect W. Because U1 and U2 are both in V, and being the subspace V is closed, U1 plus U2 is also in V. Likewise, U1 plus U2 is also in W. Since U1 plus U2 is in both V and W, U1 plus U2 is in V intersect W, so V intersect W is closed under vector addition. A similar argument shows that V intersect W is closed under scalar multiplication, so we can say V intersect W is a subspace of U. So in this week's discussion, you will be working on examining subspaces and checking sets to see if they are subspaces.